Good morning dear students, welcome back. So this is the continuation of sample question paper discussion. I have already discussed few questions from the modern physics and quantum mechanics. This is the continuation of the same module. Here is question number 2b. This question goes like this. Explain the physical significance of wave function. What answer we have to write for the physical significance? Number one, first the definition of wave function. Wave function is a mathematical function in quantum mechanics which is determined by the physical situation of the system and it is represented by psi. So physical system or quantum mechanical system means it can be a particle, it can be a group of particles, or it can be an atom, molecule, something like that. In a situation, how that particle is, what is its present status? Particle is now viewed as a wave, and that wave is represented by a wave function that is represented by psi, and this psi is essentially is a function of position coordinate and time coordinate. That means it is a function of x, y, z and t. But in this particular module, we consider only one dimension. Therefore, psi is a function of x, y and z we ignore, x and t of course. Okay. Now this wave function is also called as a state function. Why? Wave function contain all the possible information about the system. Hence it is called a state function. Such wave functions are obtained by solving Schrodinger wave equation. So when you solve the Schrodinger wave equation, you get some answer for psi. Using that psi, you can calculate position, momentum, energy, in energy, kinetic energy, potential energy, etc. Andre one particle in a complete history in a wave function kodutte. It will represent the entire status of the particle. That's why it is called as a state function. Okay, that's what the second point says. The third point also says, once the wave function is known for a particular system, physical observable quantities like energy, momentum, position, etc. can be ascertained. Wave function is a measure of probability of finding the particle, and the particle at a given position and at a time, what is the probability? Like for example, you are a particle. Let us say Ashok is a particle, or Abhishek is a particle, or Anita is a particle. And when you people are at your home, probability of finding you people in your college is 0. So when you are at home, probability of finding you at home is maximum, but at the college, in the college it is 0. Like that, probability of finding the particle keeps on changing from place to place. Like morning 9 to evening 5 you will be in the college, after 5 you will be at house. So in the college, if I try from morning 9 to 5, probability is maximum. After 5, probability is maximum at home. Itara probability changes with respect to position as well as with respect to time. Now wave functions are usually complex. This is the major problem. Wave function I told you know in the Schrodinger wave equation derivation, I wrote psi is equal to a into e to the power of minus I omega t minus kx anta barudnalla. So you notice there I is imaginary, negative sign. That means wave function is complex and negative. But probability cannot be complex, probability cannot be imaginary, probability cannot be negative. Therefore Max Born gave a suggestion, instead of taking probability alone, means instead of taking psi alone, better you take psi square. When you take psi square, that imaginary term will become negative, real. See, complex number, when it is multiplied by its complex conjugate, that complex number into complex conjugate is going to be real. So therefore you go for square, and then you take the modulus. When you take the modulus, negative also becomes positive. So this is a suggestion provided by Max Born, and hence it is called as Max Born interpretation. And according to him, don't give importance to psi alone, better you give importance to psi square, and that psi square with modulus, see here, psi square with modulus is known as probability density. So significance is this: wave function, even though it represents the probability of finding the particle, don't give importance only to psi, better you give importance to modulus of psi square, because psi alone can be imaginary, can be negative. If you take imaginary and negative probability values, you will end up with problem. Physically it is impossible, practically it is impossible. Therefore you better go for modulus of psi square. This is about wave functions and its significance. Now comes another numerical problem. This problem is on uncertainty principle. Speed of electron is measured with with measured to within an uncertainty of 2 into 10 power 4 meter per second. Delta V is given in one dimension. Of course, we talk only about one dimension. What is the minimum width required by electron to be confined in an atom? That means delta V given, delta X is required. I repeat, in this problem, delta V is given as 2 into 10 power minus 4. Width means delta X. I shall find out delta X. Well, I go ahead like this. First I will calculate P and V. You know the relation between P and V. What is P here? P is nothing but momentum, mass into velocity. Differentiate, that is delta P is equal to m into delta V. Okay, now consider uncertainty principle. Delta P delta X greater than or equal to h by 4 pi. Therefore, delta X is greater than or equal to h by 4 pi into delta P. This is nothing but h divided by 4 pi m into delta V, because delta P is already proved to be m into delta V. Therefore, delta X is greater than or equal to 6.62 into 10 power minus 34. Please follow carefully. See, I am doing the substitution. Substitution is very important. 4 into pi into m is 9.1 into 10 power minus 31 into delta V is given in the numerical 2 into 10 power 4. 10 power 4, sorry. So now let me simplify. This is greater than or equal to, well, it is 4 into 3.14 into 9.1 to the power of minus 31 into 2 to the power of 4. This is the denominator. Take it to the numerator. Multiply it by 6.62 to the power of minus 34. It comes out to be 2.89 into 10 to the power of minus 9. 2.89 into 10 to the power of minus 9. That is 2.89 nanometer. I hope you got this problem. This is on uncertainty principle. Okay, with this I go to the next module. In this module, we have questions from conduction of electrons in solids, that is quantum free electron theory and classical free electron theory, also dielectrics and then superconductors. Look at the first question. Define Fermi factor and discuss the variation of energy with respect to temperature. Well, Fermi factor. First of all, what is Fermi factor? Fermi factor is a distribution function which gives probability of occupation. See, in the modern physics also we had probability. It is probability of finding the particle. It is called wave function. It is here, it is not the probability of finding the particle, probability of occupation of the energy levels. In a container, in an atom or in a molecule or in a metal, we have various energy levels. How these energy levels are occupied, at what temperature you can find the maximum occupancy, or what is the percentage of occupancy in the level above the Fermi level or below the Fermi level. All these things we calculate through a parameter called Fermi factor, and the Fermi factor is given by this equation, 1 divided by e to the power of e minus ef by kt plus 1, where e is energy level, ef is the Fermi level, k is Boltzmann constant, t is the temperature. Now with respect to t, with respect to e, f of e keeps on changing. I just write the model. Please recall the model what your teacher gave in the regular class. The teacher might have given this type of model, on box type of model. This is the model. Okay, box type of model. This is the ground state, corresponds to E equal to 0, and somewhere here I have Fermi level, that is the highest occupied level, and all these levels are completely occupied and all these levels are vacant when the temperature is 0. Now I want to find, I want to show that all these levels are 100% occupied, all these levels are 0% occupied at t equal to 0, and also I want to see what happens if t is greater than 0. Okay, first one, case 1 is a level below the Fermi level, that means some level, just 1 minute, some level here, this is the below level means E minus EF is negative, that is what I have written here. E minus EF is equal to negative and t equal to 0. Substitute negative value and t value in this equation, then what happens? E minus EF divided by kt is negative, just 1 minute. Just 1 minute. Okay, E minus EF negative means here E minus EF is negative, divided by KT is 0. KT 0 means negative by 0. Negative by 0 means minus infinity. Anything by 0 is infinity. Now this is negative something divided by 0 is negative infinity. So 1 by e to the power of minus infinity plus 1. And you know e to the power of minus infinity is 0. So it is 1 by 0 plus 1. 1 by 0 plus 1 is nothing but 1. That means 100%. Andere, below the Fermi level, all the levels are 100% occupied. Now let us take above the Fermi level. Okay, just 1 minute. I will erase this part. It is overlapping. Just 1 minute. Now it is clearly visible. Now you consider a level which is above the Fermi level. Above the Fermi level means E minus EF is positive. This is Fermi level. Below means negative. Above means positive. So this is positive. Anyway, still it is T is 0. Temperature is 0. Now it is 1 by e to the power of something by 0. Something by 0 is positive. Now positive infinity. The only difference between this and this, it is minus infinity, here it is plus infinity. This it is minus infinity, this is plus infinity. Now it is 1 by infinity plus 1. 1 by infinity plus 1 is also 1 by infinity only, and 1 by infinity is 0. That means below the Fermi level 100% occupancy, above the Fermi level 0% occupancy when temperature is 0. Now let us take some other temperature other than 0. Let us say T is not equal to 0. When T is not equal to 0, what is the probability of occupation? Actually we have to find the probability of occupation in any of the level. Okay, this is a model, in any of the level. This is a Fermi level. You can find the probability here also, but instead of taking this level or this level, I take Fermi level itself. Fermi level I thought it is 100%, but is it 100% now also? Let me check. That is what I have done here. Please look at the calculation. What I have done, I have taken energy level exactly Fermi level. That means E is equal to EF or E minus EF equal to 0. Earlier what I did, first I took below and then negative, above and then positive. Now here itself, that means E is equal to EF, neither negative nor positive. Energy level is Fermi level, so that the difference is 0. Now in your Fermi factor formula, 1 by e to the power of 0 by something. Now T is not 0. That is very important. When T is not 0, this becomes e to the power of 0 by something. 0 by something is 0. Therefore 1 by e to the power of 0 plus 1. And you know e to the power of 0 plus 1 is 1. So it is 1 by 1. Sorry, 1 by 1 plus 1. That is nothing but 0.5. Andere, below Fermi level 100%. Above Fermi level 0%. Fermi level 100%. When? In the previous case, temperature 0. Now scenario is not same. Fermi level I cannot say it is 100% occupied. That is what I have got here. Fermi level is how much occupied? 50% occupied. How much vacant? 50% vacant. So these results are graphically represented here. Look at the green color curve. Green color curve represents the occupancy at 0 temperature. 0 temperature ali up to Fermi level 100%. 100% means 1. Afterwards 0%. Red color represents temperature greater than 0. Up to Fermi level, not up to Fermi level. At Fermi level it is 50%. That means already electrons started going up. So you can see some vacancies even below the Fermi level also. So this graph you have to mention. For graph 1 mark is reserved. Well, with this I move on to the next question. Now comes question on superconductivity. Describe Meissner effect and hence classify superconductors into soft and hard. Soft andre type 1 anta, hard andre type 2 anta. Adhe question annu hangu kelbodu. Distinguish between type 1 and type 2 superconductors ಅಥವಾ soft and hard superconductors. Okay, first of all, what is Meissner effect? See, when you keep a superconductor in the external magnetic field, right, and reduce the temperature, magnetic lines which are passing through the specimen will be thrown out. That means when the superconductor acquires a superconducting property, it will not allow the magnetic lines to enter. It behaves like a diamagnet. This was noticed by Meissner, hence it is called as Meissner effect. Provided applied magnetic field should be less than critical field. If the applied field is too much, tumba jasti idre, it will not see whether it is a conductor or superconductor. It simply penetrates through the substance, and the critical field is able to spoil the superconducting property. Only if the field is less than the critical value, then it will not enter, it will pass by the side of it. That means superconductors behave like a very good diamagnets if the applied field is less than critical field. This is what I have given in the wordings here. When a superconductor above the critical temperature is placed in the external magnetic field, it allows field lines to pass through. First allow madutte. If now it is cooled and the temperature is reduced below the critical temperature, magnetic lines are expelled, thrown out, kicked out from the substance. This is known as Meissner effect. Alge Meissner effect question ge answer aitu. Now distinguish between type 1 and type 2 superconductor. First of all, type 1 andre eno? Superconductors having only one critical field are known as type 1 superconductors. One critical field. The transition from superconducting state to normal state occurs sharply. If you increase the magnetic field, suddenly it will convert from superconductor to normal conductor. Okay, this is type 1 superconductor speciality. And they exhibit complete Meissner effect. And if you keep the type 1 superconductor in the external magnetic field, either they will allow the magnetic field or they don't allow the magnetic field. No bargain, partial allow madak prashnene barodilla. Either they will allow or they will not allow. If they don't allow, there is no question of magnetic field inside the specimen. So it is a perfect diamagnet, means perfect Meissner effect. That is the meaning of this sentence. They exhibit complete Meissner effect. Next, magnetization grows proportionately and drops suddenly. Look at this graph. Intensity of magnetization keeps on increasing. MH anta helidare nanalli I anta bardidini. Please you can change this I to M or you can retain I also. Intensity of magnetization. Negative intensity increases and suddenly drops. Please watch my video on superconductors. All these details are clearly explained. Here just because of the paucity of time, shortage of time, I am not going in detail. I am just giving you idea about how to answer, how much answer you are supposed to write. Okay, for understanding what is I, why it is taken as minus I, please watch my video. Okay, this graph is very important. You please mention the graphs, draw the diagrams, write the equations wherever and whenever they are required. They carry more weightage. Okay, even if you forget to write the sentence, if you draw the diagram, it gives full meaning. Okay, and they are called very soft superconductors because Hc value is very small. Hc is tumba kadime irodinda they are called as soft. That means they can be spoiled easily. Soft and it is not that soft like sponge. It is not physical softness. Whether they can surrender to the magnetic field or do not surrender to the magnetic field. In that sense they are treated as a soft or tough, soft or hard. So this is about type 1 superconductor. Type 1 superconductors, only one magnetic field, perfect Meissner effect, sudden change, they exist either in superconducting state or normal conducting state, and their critical field is very small, therefore they are called soft superconductors. Quite opposite to this is hard. They exhibit two critical fields, Hc1 and Hc2. Look at the graph. Initially they behave like type 1 only. But instead of falling suddenly like this, they start falling gradually, and after a larger value, intensity becomes 0. That is at higher value of H. So this is the point where downfall starts, and this is the point where I becomes 0. And the decreasing trend starts here, decreases to 0 here. This is Hc1, this is Hc2, and Hc2 is very much greater than Hc1. Therefore, they are called as hard superconductors. And these superconductors exist in 3 states: superconducting state, normal state, in between mixed state also. Here they are partially superconductors, partially normal conductors. In fact, they allow magnetic lines partially to pass through. Therefore, you can say type 2 superconductors do not exhibit complete Meissner effect. Now you list out, ನೋಡಿ explain ಮಾಡಿದೀನಿ, ನೀವೇ list ಮಾಡಿ. Type 2, 4 ಪಾಯಿಂಟ್ ಹೇಳಿ. Number 1, they have two critical fields, Hc1 and Hc2. They exist in 3 forms: superconducting form, mixed form, normal conducting form. Next, they do not exhibit complete Meissner effect. Next, Hc2 is very much greater than Hc1, therefore they are called as hard superconductors. Dear students, I hope you are following. I am little bit fast, but I hope you can manage with this speed. Anyway, answers also will be given at the end of the discussion of all these questions. Please download that PDF forum and practice it. Okay, now let us move on to the next question, that is question number 3C. Calculate the probability of occupation of energy level 0.02 electron volt above the Fermi level. That means you have to find out F of E at a temperature of 27 degrees centigrade. 27 degrees centigrade is as good as 300 Kelvin. Remember, always we have to take temperature in Kelvin, not in Celsius. Even if it is in Celsius, you convert that into Kelvin and then do the calculation. Well, the formula is actually you have to find out F of E. F of E question mark. Here E minus EF is given as 0.02 electron volt. He says it is above, therefore this is positive. Okay, and then temperature is 27, that is nothing but 300 Kelvin, because 27 plus 273. Well, the formula is F of E is equal to 1 divided by E to the power of E minus EF divided by KT. K is Boltzmann constant plus 1. Well, I first calculate E minus EF by KT separately. E minus EF by KT is equal to 0.02 into 1.6 into 10 power minus 19, because I have to convert electron volt into joule, divided by K is 1.38 into 10 power minus 23 into temperature is 300. Well, just wait, I will do it for you. 0.02 into 1.6 to the power of minus 19 divided by 1.38 to the power of minus 23 into 300. It is 0.7, one second I will do, 0.02 into 1.6 into 1.6 to the power of minus 19. This is numerator, divided by 1.38 to the power of minus 23 into 300. Well, it comes out to be 0.772. So this is 0.7729. Therefore, F of E is equal to 1 divided by E to the power of 0.7729 plus 1. That is, so I have to take the exponential of this. Exponential of this is 2.166. So it is 1 divided by 2.166 plus 1. Okay, well, simplify this now. It comes out to be 0.32. 0.32. That means 32% of occupancy, where in a energy level which is above this Fermi level. How much above it is? It is above by 0.02 electron volt. ಇಷ್ಟು ಮೇಲಿರ್ತಕ್ಕಂಥ ಎನರ್ಜಿ ಲೆವೆಲಲ್ಲಿ ಎಷ್ಟು ಪರ್ಸೆಂಟ್ ಆಕ್ಯುಪೆನ್ಸಿ ಇದೆ? ಅರೌಂಡ್ 32% ಆಕ್ಯುಪೆನ್ಸಿ ಇದೆ. ದಿಸ್ ಈಸ್ ದ ಪ್ರಾಬ್ಲಮ್. ಓಕೆ, ಐ ಹೋಪ್ ಯು ಆರ್ ಫಾಲೋಯಿಂಗ್. ನೌ ಲೆಟ್ ಮಿ ಪ್ರೊಸೀಡ್ ಫರ್ದರ್ ವಿತ್ ದ ನೆಕ್ಸ್ಟ್ ಮಾಡ್ಯೂಲ್. Next module, question number 4. This is about, sorry, not next module, this module only, next question. Question number 4. I am still in module number 2 only. This is about discussion of different types of polarization. You know, in dielectrics there are different types of polarization mechanisms. After all, what is polarization? Polarization is nothing but net dipole moment per unit volume. If you increase the dipole moment by some methods, then you can say the whole material has got polarization. You increase the dipole moment either by orienting the dipoles, or by reshuffling the atoms, or by rearranging the electronic configuration, or by moving the electron cloud. Do whatever you want, but overall dipole moment should increase. On this basis, we have 4 classifications. We have identified 4 types of polarization mechanisms. They are: number 1, electronic polarization. See, this normally happens at the atomic level and it mainly occurs in inert gases. What is electronic polarization? See, in an atom we have positive cloud, positive charge due to nucleus, means protons, and around the nucleus electrons are revolving, that is negative. So under normal condition, positive and negative are one above the other. That doesn't mean that electron is sitting on the proton. Overall effective center of the positive charge overall effective center of the negative charge coincides, so they are one above the other. Now you apply the electric field, they move little bit, entire electron cloud may shift this side or it may shift this side. When the shift occurs, there arises dipole. Therefore, dipole moment comes into picture, polarization takes place. This is happening because of the shifting of electron cloud, hence it is called as electronic polarization. See the statement, sorry. The explanation goes like this. Please read the explanation. The electron cloud of atoms or molecules displaces slightly with respect to fixed positive cloud. Idenne nanu helidu, positive cloud we cannot shift, nucleus you cannot shift, only electron cloud you can shift like that, like this, like that, like this. Okay, so with respect to fixed cloud, if you shift in the presence of external electric field, dipole moment increases. This is known as electronic polarization, and of course it is independent of temperature. You cannot disturb this type of moments by increasing the temperature, because atoms are almost undisturbed by the temperature at normal values. At a very high value they may get disturbed, thousands of degree adaga atoms disturb agbodu. Normal temperature alli hundreds of Kelvin iddaga atoms gu temperature gu connection irodilla. Okay, next comes ionic polarization. In case of ionic crystals like sodium chloride, potassium chloride, etc., ಪಾಸಿಟಿವ್ ಅಯಾನ್ಸ್ ನೋಡಿ, ಇದು ಎಲೆಕ್ಟ್ರಾನ್ ಇಂದ ಆಗೋದಿಲ್ಲ, ಅಯಾನ್ಸ್ ಇಂದಾನೆ ಆಗುತ್ತೆ. ಇನ್ ಕೇಸ್ ಆಫ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಯು ಹ್ಯಾವ್ Na plus, you have Na minus. When you apply the electric field, Na plus, Na minus, sorry, Cl minus, Na plus, Cl minus, sorry, Na plus, Cl minus, they move away or towards each other due to applied electric field. As a result, dipole moment comes into picture. After all, what is dipole? It is a combination of two equal and opposite charges separated by a small distance. Sodium and chlorine, positive and negative. Suppose if they move little bit apart, then dipole comes into picture. So this is due to movement of the ions, hence it is called as ionic polarization. I repeat, in ionic crystals, positive and negative ions move in the opposite direction in the presence of external electric field. This is known as ionic polarization. Next is orientation polarization. In some materials, especially polar dielectrics, already dipoles will be present. Only thing is they are in a random orientation. Random agi akade ikkade orient agirtave. If you apply the electric field, they start orienting. This is very important polarization mechanism, and the orientation depends on temperature. If temperature increases, again there will be disturbance of orientation. So dipole moment coming due to orientation of the dipoles is known as orientation polarization. It is inversely proportional to temperature, and this normally occurs in polar dielectrics. Adike ನಾನು beginning alle helidini, in case of polar molecules, even though there exists individual dipole moment, the net value is 0 due to random orientation. When external field is applied, they rotate about the axis and the net dipole moment increases. This is known as orientation polarization. It is inversely proportional to temperature. Okay, space charge. This is a peculiar and very rare happening. If at all any defects are present inside the material, some boundaries are present inside the material, charges gets accumulated over there and there arises polarization. This is also one contribution, but it is a very small contribution. Major contribution first three only, right? The diagrams are like this. You see, in the first case, this is electronic polarization, both positive and negative. This green cloud is negative, this one is positive, so they are overlapping. If I apply the electric field, the negative cloud is shifting this side, therefore there is a dipole moment. Next, coming to second diagram, the charges are well arranged, sodium chlorine, sodium chloride, sodium chlorine, sodium chlorine, like that. But if you apply the electric field, so there arises dipole formation. Okay, some of them go near, some of them go like this, dipoles are recreated. This is ionic, and see, orientation is clearly visible. See, our dipoles are randomly oriented, but when you apply the electric field, they start orienting in the same direction. So this much you have to write about the different types of polarizations. Now coming to the Clausius-Mosotti equation. This is also one of the expected question. Clausius-Mosotti equation for solid dielectric material. Well, dear students, I just run through the steps. This equation relates the macroscopic quantity called dielectric constant with microscopic quantity called polarizability. Epsilon r matte alpha relation. Epsilon r is for dielectric constant, alpha is for polarizability. Okay, now consider one non-polar dielectric material applied with electric field E. When you apply electric field inside the material, let us say this is a non-polar dielectric slab. ಇದಕ್ಕೆ ನಾನು field ಅನ್ನು apply ಮಾಡಿದಾಗ inside the material there arises a new type of field called internal electric field. Okay, so you might have already heard of internal electric field. ಒಳಗಡೆ internal ಆಗಿ ಮತ್ತೆ ಒಂದು electric field generate ಆಗುತ್ತೆ due to polarization of the charges, polarization of the dipoles. Okay, already what are the polarization mechanisms I explained in the previous question. Okay, now we have polarization connected with the internal field. P is equal to n alpha into EI. Alpha E stands for electronic polarizability. We are talking only about electronic polarizability. Okay, so n is number of dipoles, EI is the internal field. After rearranging, I get EI is equal to P by n into alpha E. Okay, now we have this relation between polarization, dielectric constant and applied electric field. Please remember all these equations, and one suggestion I would like to give: in the handbook what equations you get is only for solving the numericals, not for deriving the equations like this. Therefore my suggestion, please practice all the derivations once or twice. In physics there are about 20 to 25 derivations, smaller one, bigger one, from all the modules. ಎಲ್ಲಾನು ಕೂಡ ಒಂದು ಸರ್ತಿ ರಿಹರ್ಸಲ್ ಮಾಡಬೇಡಿ. ಬೆಟರ್ ಯು ಸ್ಪೆಂಡ್ 1 hour ಎಕ್ಸಾಮ್ ಹೋಗೋ ಮುಂಚೆ ಹಿಂದಿನ ದಿನ ಮತ್ತೆ ಅರ್ಲಿ ಮಾರ್ನಿಂಗ್ ಬೆಳಿಗ್ಗೆ ಎದ್ದು ಒಂದು ಸತಿ ಎರಡು ಸತಿ ರಿಹರ್ಸಲ್ ಮಾಡ್ಕೊಂಬಿಡಿ ಡಿರೈವೇಷನ್ಸ್ ಅನ್ನ, ಇಲ್ಲಾಂದ್ರೆ ಮರ್ತೋಗೋ ಚಾನ್ಸ್ ಇರುತ್ತೆ. Okay, so derivations always fetch you full marks. Okay, so in derivation we make use of some additional equations. That's why I am asking you to revise the derivations once or twice. Okay, I have P here. From this I rewrite E is equal to P by epsilon naught into epsilon r minus 1, and this entire thing comes here. Now this is another equation. This is the expression for internal field. Nodi EI is equal to E plus something. E plus something. Now I have EI, that is equation 1. I have E, that is equation 2. Well, let us substitute equation 1 and 2 in 3. Substitute equation 1 and 2 in 3. You get this formula. EI, that is equation 1. E, that is equation 2, plus P by 3 epsilon naught. Now you keep on simplifying, cancel P on both the sides, right? You get this formula. P cancel ಮಾಡಿದ್ರೆ ಇಷ್ಟು ಉಳಿಯುತ್ತೆ. Now in the RHS I can take epsilon naught as common factor in the denominator, right? And remaining two steps are self-explanatory. Just to watch them, you will get an idea. What I have done here, I have taken LCM, and epsilon naught I sent it to LHS, so it is in the numerator. Numerator of the RHS will be epsilon r plus 2. How it is plus 2? Take a pen and paper, do it, right? You can stop here itself, or you write one sentence, just one sentence, or one step further. That means 3 you take here, right? 3 you take here, then take the reciprocal. Even if you don't take reciprocal also, even if you stop here also, it is considered as Clausius-Mosotti equation. Look at the final equation. I have epsilon r, I have alpha E. Epsilon r is macroscopic parameter, alpha E is microscopic parameter. So from the Clausius-Mosotti equation I get lot of information about the electronic arrangement, electronic polarization, type of the dielectric, whether it is polar or non-polar. All these things I can find out. Therefore Clausius-Mosotti equation is more important equation in dielectric materials. Well, with this I move on to the next question. Question number 4C. This is again numerical. This time we have question on superconducting material. Lead has superconducting transition temperature 7.26 K, Tc given. If the initial field is 15 to 10 power 3 ampere per meter, calculate the field at 6 Kelvin. I told you, no, superconducting property can be spoiled. Just 1 minute. Superconducting property can be spoiled by applying the external magnetic field. How much field we have to apply and how it depends on the temperature, all these informations are given in this equation. That is H is equal to, how much field I want to apply, is equal to Hc naught, that is a field at 0 Kelvin, into 1 minus T by Tc whole square. Okay, this is also one of the important concept. In fact, if you plot H versus T along x-axis, H along y-axis, the graph looks like this. When T is equal to Tc, H is equal to 0. When T is equal to 0, H is equal to maximum, that is Hc0. This entire portion represents superconducting state and this is normal conducting state. Coming back to this formula, H is equal to Hc0. What is Hc0 value? It is 50 into 10 to the power of 3 into 1 minus T is 6. Tc is 7.26 whole square, close the bracket. Now simplify. First I will simplify 6 by 7.6 comes out to be 0.789 and square of that, and then minus 1, okay, into 50, that is equal to 18.83. so finally I get answer as 18.83 into 10 to the power of 3 ampere per meter. So this is about question number 4C. Well, dear students, with this I conclude this particular module. I will come back immediately with the remaining modules. Okay, I just want to make only short duration videos, not more than 30 minutes. Sometimes it is exceeding 30 minutes. Please bear with me. Okay, and we watch videos in this order only. First one, next second one, next third one, in that order only you keep watching. And also share your comments. Thank you. Thank you very much.